Welcome to the first lecture on data in our AT course. So today we're going to talk about data collection and processing. And since this is very closely related to sensor data processing and embedded systems hardware, I took the liberty to borrow some slides from my old boss, Peter Marbedel from TU Dortmund. So if we talk about data in the Internet of Things, we first think about data that's going to be collected and processed in the IoT. So, very many devices at the edge of IoT systems have a large number of different sensors, and these sensors are there to collect data, and this data can optionally be processed on a device or offline or somewhere in the cloud. So, we have this diagram of data in the Internet of Things in general. So, we start at the bottom today with a discussion of IoT sensors and a bit of devices and very few actuators. We'll talk about IoT sensor data and what is involved in processing this data, how we can actually acquire it. And we'll talk about a bit about data processing in the IoT, especially about data denoising today, but on this higher level. So the first level of data processing, there's also additional things to do, like, for example, outlier detection. So detecting if one of the measurement values is just completely out of bounds. So we would assume like a sensor failure or something like that. If there are data missing because the sensor was not recording data for some time, we might need to just like interpolate data, for example, to figure out which data was missing. And we could also already want to aggregate some data before we send it out into the cloud somewhere. Then on the next level above is IoT data fusion. So we have different sensors capture different probabilities, have different properties, like a different precision. They measure different physical physical properties, physical sizes. And this means that by combining data about the same effect we're going to measure from different sensors, we can get not only a different view, but we all can also get a more precise view of what's really going on in our environment, which is what we intend to capture in our IoT application. And from there on, we have lots of data or data streams. So from these data streams, we can try to generate knowledge and of course, then finally make decisions. So, for example, we can measure temperatures and we can have a sensor that figures out the occupancy of a room. And like if the room is cold and there's somebody in the room, we can figure out, as a very simple example, that we should turn on the heating. And in general, this knowledge generation can be backed by a large amount of data, like platforms in cloud computing that can store data and also run more complex models depending on what you have to simulate or to do. Like if you want to, for example, detect persons on a camera, that's a task that you might not want to do at an edge device, which just has little computing power. That's something you might probably want to give to a device in the cloud as a task. And on the other hand, you have solutions that help here, like deep learning and machine learning approaches that can help with especially more complex recognition tasks, which are more and more common as sensors get more complex. So you want voice recognition, face recognition, and similar things here. So today we're going to talk about sensors first. And to do that, we should look at where sensor data is actually used in an IoT node. So what we see in the picture here on the lower right-hand side is a very typical IoT node or embedded systems. In this case, it's pretty similar. So what's important is this is not just a device that's standalone. It's sitting inside of a physical environment. So the first thing it should do is it should use its sensors to capture information from the physical environment. So here we've just shown a microphone, for example, but it could be anything you can imagine, like an acceleration sensor, a temperature sensor, and yeah, light sensors. There's large amounts of very different sensors for almost all sorts of physical properties out there. Now, these sensors usually convert a physical effect, whatever it is, to an electrical signal, and usually these electrical signals are analog in nature. So these analog data have to be converted into digital data, and we'll talk a bit about this in detail in the upcoming slides. And Finally, we can do the information processing. So this is the part where our computer comes in, where we have a microprocessor, software running on it, and memories. And as a result of the information processing, we have a display. What's not shown here, of course, we have a wireless interface to send out data. And we might also have actuators to control, for example, using a digital to analog converter if we have analog motors, or we might even simply control very simple digital devices like an LED using pulse width modulation for an LED lamp that we want to control over the IoT. So what we have here in general is what we call hardware in a loop. So essentially, by measuring things from the environment, processing this data, and then using an actuator, for example, if this would be a mobile robot, we would change our view of the environment because we would have moved to a different place in our environment. So we can sense something new. Of course, the IoT extends this model by enabling you to do the information processing not only on device, but to separate this. So you can have sensors on one device, you can have the information processing somewhere in the middle, and you can have another device which is controlling the actuators. So one simple example is again in home automation. So if you have a light sensor as a separate device and an IoT light bulb as another separate device, then of course you can provide it that the light sensor sends information about the current lighting conditions to a controller somewhere in your IoT network, and this controller decides to turn three of your IoT controlled lamps on. And of course, there are large numbers of examples for these control loops, heating and lights. In cars, you have engine controls, you can have power supply, and of course, in more complex things, we have complex sensors, maybe even image sensors, LiDAR sensors to sense your 3D environment, and so on. This is used in robot. The challenge for the IoT, of course, is that this is no longer constrained to a single embedded device, but in the IoT, these control loops can be distributed over different IoT devices, and we have to get them to talk to each other and to work together. So, when we talk about sensors, we want to process some data from our physical environment, and of course, to do this, we need to capture this data somehow. And as we've already seen, sensors can be designed for almost every physical and chemical quantity, like weight, velocity, acceleration, electrical current or voltage, temperatures, and in recent times also chemical compounds. So one of the interesting developments that have come up recently are electronic noses. So you can finally sniff out molecules of the environment, for example, to find harmful chemicals or drugs or whatever you can imagine you want to automatically detect somewhere, which is a chemical component. And depending on what you want to measure, you usually try to select a physical effect that transforms this quantity you're going to measure into an electrical signal, so usually a current or voltage. And this can be used like with the law of induction, so you could try to generate voltages in an electric field when something moves, or you could use light electric effects, for example, for photosensors. And especially in recent years with IoT and robotics really increasing in relevance, there have been a huge amount of sensors designed and developed. So nowadays, when you can go out, you can find a sensor for almost everything, even including very complex stuff like 2D, 3D image and video recognition. That's pretty amazing. So, what does our sensor generate? So, if we abstract, our sensor data is what we call a signal. And a signal, let's define this precisely, is a mapping from a time domain, which we call dt, to a value domain, dv. So a signal S is a function that maps a point in time from a time domain dt to a point in our value range dv. Now these time and value ranges in the real life, let's ignore quantum effects and quantization of time, in our macroscopic view of the world, they are continuous. So we don't have ticks indicating time. Our time flows constantly. And again, we don't have separate levels of voltages, for example. Our voltage, when we ramp it up from 0 to 5 volts, just ramps up without leaving out an intermediate value. That's physically impossible. So what we usually have first is always continuous time and value here. And due to this mapping, we know the relationship, so we know at which point in time which value was measured by the sensor. Now, this is analog, and the problem is that our computers don't really work well with analog signals because they are clocked in finite time steps. So each instruction takes whatever, a nanosecond or a fraction of a nanosecond. So capturing anything in between that might be difficult. And we also have discrete numbers. We have binary numbers. Binary numbers have a fixed precision, no matter if they're integer numbers, fixed point numbers, or even floating point numbers. In floating point numbers, you have a large amount of variability to give you a value range, but nevertheless, there's only so many digits behind the decimal or binary point that you can have and store, because to store an infinite precision, well, you would run out of memory pretty soon, obviously. So what we have to do is we have to what we call discretize these signals in order to use them in our computer, so in turn in our IoT system. So the first thing we have to do is discretization of time. We need these discretization of times, so we need measurement values at certain intervals of times because we can't handle the amount of data with an infinite change in between. So essentially what we want to do is we want to look at our signal at certain steps of time. So our signal function stays the same at first. It's still a mapping of dt, our time domain, to dv, our value domain. But now the values of dt are constrained to only values that are, for example, a certain defined amount of time apart from each other. So for example, we want to measure a value every 10 milliseconds. And in order to do this, we actually have to consider that the process of measuring a value is not instantaneous. It takes some time. So we need a way to actually keep the value that we're going to measure constant for this small interval we're going to measure it at. So for these 10 milliseconds. And this can be done with a so-called sample and hold circuit. So this is a circuit that essentially stores a value at a given point of time when given a signal, and stores it as long as well, the time is required to measure it. And then when the next tick comes, you need your next sample, your next step of your discrete time domain, then it's going to sample the next value. How does this work? So here we're going a bit into very simple electrical engineering. So essentially what we want is we want a signal which is a voltage. And we see this on the right-hand side here. So this black line is just our continuous signal from a continuous time domain to a continuous value domain. So we have t on the x-axis and our values on the y-axis. And our signal E of t is actually the analog signal, an analog voltage coming in from our sensor. And what we want is, if you look at the dotted lines here, we only want the samples at these points in time. So we want another function derived from E of t, which we call h of t, which only has values at these defined points of time. So for this, for example, if you look at the very first dotted line next to the y-axis, we need to keep the value that's at that point of time constant until we are able to measure it. Because otherwise we'd measure something in between, because the value doesn't stay constant until the next point in time we're going to measure it. And this is done by the circuit on the left-hand side. So we have our input signal E of t coming in on the top left-hand side, and this is going through a transistor. So this circuit element there, which has a clock on the bottom side, is modeled like a MOSFET transistor, so a field effect transistor. And this field effect transistor works like a switch. So in a switch, you can switch on or off a signal. And usually this is done with a light switch, of course, manually. And in a transistor, you can do this with an electric signal. So what we do is we can provide a clock. A clock is just a rectangle signal, which is active at each of these points in time where the dotted lines in the right-hand signal are. So for a very short amount of time, this clock enables your transistor as a switch. So this means our signal E of t can propagate from the left-hand side over the transistor to the right-hand side. There, it's actually connected to a capacitor. So the capacitor is the two parallel lines on the right-hand side, and this capacitor can store charge. In essence, if we take it very simply, it remembers the voltage at that point of time. And then we switch the clock off again, and our capacitor keeps the voltage there. So we can now measure it on the other side, and this gives us h of t. And then this voltage stays constant until we measured it, and then the next clock cycle comes, so our capacitor is charged or discharged until it stores a charge appropriate to the next voltage level we want to measure, and so on. So what we achieve using this very simple sample and hold circuit is we transform our signal from E of t, which is a mapping from real numbers to real numbers, so from a continuous time and value domain, to a sequence of values. So a mapping of from Z, so just discrete, maybe integer numbers. So you just count steps, so 0, 1, 2, 3, and then you multiply them with, for example, 10 milliseconds. So you can easily say it's a mapping from just discrete numbers and steps, but we still have real numbers in the value domain. So we still have continuous values in the value domain that we have to work with. But nevertheless, this is the first step we have to do. So now, using the sample and hold circuit with an appropriate clock, that should obviously be as fast as our data acquisition system is able to work. Now we can have discretized analog values at certain amounts of time. So if we do this sampling, we need to ask ourselves, we have all this information between these sampling points. What's going to happen with these bits of information? So are we actually losing information due to the sampling? Or let's ask the other way around. If we only have samples of a signal, would we actually be able to reconstruct the original input signal from only our discrete time, continuous value, signals we have measured over our time interval using our sample and hold circuit? And now we're going a bit into signal theory, so sorry, it gets a bit mathematical. So if you are an electrical engineer or have some electrical engineering background, you've of course all seen this, discrete cosine transforms and stuff like this. And for all others, we can say that all signals that we can generate can actually be generated by summing up sine waves. So you see a sine wave there on the top right hand side. And these sine waves can have different frequencies. So we have a sum over a sine, and this sine has a parameter which is dependent on a value k. And this k is increasing over the sum. So first we have a sine wave of a basic frequency, k equals 1. And then we take the next element of the sum for k equals 3. So we have a sine wave with 3 times the basic functionality, and we add it up. So if we have our original sine wave here, which has this large amplitude here, then if we add another sine wave with 3 times the frequency on top of it, you see that we already have something that has much sharper changes in the signal from high to low, so from 1 to -1, for example. And you see this triple frequency sine wave on top and on the bottom of our combined wave for 1 and 3. And of course, we can continue this. So we can add a sine wave of even higher frequency. So now let's take a factor of 5 from the original frequency. And you see, we get something that looks more and more like a rectangle signal. And a rectangle signal is something, well, an ideal rectangle signal does not exist in the real physical world, but we can approximate it. And you see, as we add more and more of these elements, of these sine waves, with higher frequencies, we can reconstruct something like a square wave, a rectangle signal, better and better. And in the end, for k equals 11, that doesn't sound so bad. And this is also what you see when you look at a rectangular or square wave with an oscilloscope. You see these signals are over and undershooting for a bit, so they won't stay at the exact equal level of 1 and -1. And there's also no perfect vertical line going from 1 to -1, because that would mean you could transfer charge infinitely fast. If you could do this, you could build a perpetual mobile, but that's unfortunately impossible. So it needs some time to do this, but you can do this better and better. So this means you can sum up sine waves of different frequencies and you can stop somewhere. And depending on where you stop, that's the precision you get for reconstructing your output signal. So if you only start with k equals 1, then you get only a sine wave, which is not a very good approximation of a square wave. But if you increase k to 11, so you add just 1, 2, 3, 5, 7, 9, 11, so 6 different sine waves here, then you get a pretty good approximation already. And of course, that works the other way around. So if we sample at a frequency that's high enough, we usually get samples that capture parts of these frequencies good enough so that we can actually try to reconstruct our signal in the end. So what we're considering here is what we call linear transformations. So let's consider two signals again, and we call them E1 of 2 and E2 of 2. And now we consider a constrained version of functions operating on these signals. So this is a bit of advanced mathematics. So we have functions operating on functions here. So these functions we want to consider here are so-called transformations. And a transformation of a signal can have properties. And we want to have a special property, which we call a linear transformation of a signal. And a linear transformation a transformation is called a linear transformation if, and this if with two F's, you might have seen it before. It's not a typo. That's a computer science shorthand for if and only if. So exactly that condition must hold. And which condition must hold here? Now, if we sum these two signals together, like we did with our sine signals before, then the transformation, so a function we apply on these two signals added together, must always result in the same value as if we first apply the transition to each of the signals E1 and E2 individually and then add both together. This is an important property. We won't go into too much detail here because otherwise we'd spend a semester discussing mathematics, which is interesting, but not really in the topic of that course. But it might be interesting or important for some of the understanding here. So in the following, we will only look at transformations which are linear transformations. And instead of the original signal coming in, we consider sums of sine waves that are constructing or reconstructing an original signal as we've seen on the previous slides. So what problems can show up? Now, let's assume we have two different signals here. We have a signal E3 of t, which is the black line. E3 of t, you see, has a relatively low frequency. And we have another signal, which is the dotted line, which is E4 of t. And you see E3 of t and E4 of t are relatively similar. So E3 of t is a sine wave added to a sine wave of twice the frequency. Whereas for E4 of t, we have the same first two components, and that we add another component with 4 times the frequency of the second term here. So we have 3 periods of sine waves here, 4, 8, and 1. Now, what happens if we sample this signal with a very slow or relatively slow sampling frequency? So our points shown on the x-axis here, and the blue lines are then our sample time points and the sample values on the y-axis. And what happens here is, you can see at all sampling points, the sampling values for E3 of t are identical to the sampling values of E4 of t. And the only things we are going to receive from our sensor are the sensor values at these sampling points. So we don't see what's in between. So what happens here is, if a frequency of a signal or part of a frequency of a signal is too high compared to our sampling frequency, then we cannot really notice what's happening in between these sampling points, and a function that has a higher frequency part, like E4 of t, appears to be a function of a lower frequency. So this is called aliasing, because one function with a higher frequency component is aliased or looks like this black function E3 of t with a lower frequency component. So this is one of the general problems when you are trying to discretize time, that you need to adapt your sample frequency to the properties of your signal, so to the highest frequency of the signal that you're going to measure. So you need to know something about your signal. And in very many times or very many circumstances, you know it. So let's assume for audio signals, if you want to, for example, record human voices, you might be happy with a frequency range of human voices between 0 hertz and 20 kilohertz. So you know the highest frequency that can come in is 20 kilohertz. So let's look at in a bit what happens when we want to sample this. Well, the problem is, as we've seen, a reconstruction of the original signal, like our high-frequency part E4 of t, is impossible if we are not sampling frequently enough. And the question is, how frequently do we have to sample? And this is defined by the so-called Nyquist criterion, or sampling theory. And this says that aliasing can be avoided if we manage to restrict the frequencies of the incoming signal to be less than half of the sampling rate. So this means in each period of our incoming signal, we have at least 2 measurement points. So we measure at least twice in each period. And this enables us to at least correctly reconstruct our signal concerning the frequencies. For correctly or more correctly approximating the amplitudes, you might need a higher sampling frequency. Now, this is a general idea. So when you want to sample a signal of a frequency f, you need a sampling frequency of more than 2 times f. So that's exactly the Nyquist frequency. So f is the Nyquist frequency, which is the highest frequency, and fs is the sampling rate here. And essentially, you need to ensure that you measure twice per period of your incoming signal. So the fastest sine wave, which is always guaranteed to be periodic, of course, or the other way around, the frequency of the fastest sine wave must be less than half the frequency of your sampling. Of course, we can't go into too much details here. There's lots of literatures out there, like the Engineer's Guide to Signal Processing, which is open source on the internet, so you can just freely read it, and it's very well readable as literature reference 3 here. So what can we do about aliasing? Of course, we uh, can force a signal. What we can do is we can force a signal to actually not have any higher frequency components than half of our sampling rate. And to do this, we need something we call a filter. So essentially, in our advanced signal input processing chain, we still have our sample and hold component on the right-hand side here, and now we have an anti-aliasing component, our filter, in front of this. So a filter is an electronic circuit consisting of resistors, capacitors, and inductors, which can help by storing and transforming electrical energy in general to just filter out higher frequencies because it just doesn't react quick enough. So what we see on the lower left-hand side here, the right dotted line would be an ideal filter. So what we have here on the y-axis is the relation of the output signal of the anti-aliasing filter to the input signal. So ideally, this should be 1 for all signals with a frequency of less than half the sampling frequency. So they should be transferred to the right-hand side of the anti-aliasing filter undisturbed. And everything above should have an amplitude of 0. So essentially, we mute our audio level, for example, down to 0 for every frequency that's higher than or equal than than half our sampling rate. Now, unfortunately, like with our rectangle signals, it's impossible to generate an ideal filter because we need to transfer charges again, and this takes time. So a realizable filter rather looks like a black line here in our lower left-hand side diagram. So a realizable filter already drops off early before we reach half our sampling frequency. So, for example, this would mean frequencies that are closer to our sampling rate in an audio signal are not as loud, so the amplitude is going down. And then what's maybe even worse is that we have still parts of the amplitude on the right-hand side of half of your sampling frequency. They're pretty quiet if we have an audio signal, but they still exist. So it's just approximating 0, but it doesn't reach it there. And if you wanted to reach it value very close to 0, then you'd have drop off very early. So filter design is a complex thing in itself. We don't go into details here, but I think the takeaway is that you can't build an ideal filter, and you need experts on analog signal design or mixed signal design essentially to build these filters in electronic circuits, but you can also build filters in software using signal processing. Now, what does this filter do when we actually apply our high frequency signal E4, the dotted line, to the filter? So this is our E4 of T. Now, it essentially removes the high frequency component if we configure the filter correctly with a cutoff frequency of fs half, and we get our black line out. So essentially this anti-aliasing filter does not magically add information about high frequencies. That's physically impossible. It just removes these to ensure that whatever we measure is in the frequency range we expect. So this is very useful when you have high frequencies, for example, due to electromagnetic interference coming in, something like this, which you want to filter out because they're not actually part of the original signal. And if you would also measure them here, you would get aliasing effects, and that would change your measurement outcome. So these circuits are very useful to have. And you've maybe seen this before, examples of aliasing. We have an example of, just a two-dimensional picture taken with a digital photo sensor here. And on the left-hand side, we have the original picture of a brick wall, and you can see the bricks are pretty regular, and the distance between the bricks looks the same. And if we do subsampling, so we reduce the resolution and we don't do any filtering on this signal, we get what's shown on the right-hand side. And you've probably seen this with bad cameras and stuff like this. This is a so-called moiré effect. So the distances between the single bricks now don't look even anymore, but they're changed. And that's because some of these white lines fill in exactly a pixel. Some of these don't fill exactly in one of the pixels. So essentially they appear wider or narrower, and in turn you have these lines or these bands of curves which appear to be more or less lit, or it appears like there's a wave going over your wall. And that's what's happening due to subsampling without frequency filtering. And that's a problem not only in digital picture processing, but of course in all sorts of signal processing. Okay, so now we have discretized time, and we know how to get around our biggest problem of of signal frequencies that are too high for our sampling frequency. So now we have to consider the other domain, the value domain. So we need to discretize values, usually voltages, into, just values, digital numbers that our computer can process. So we cannot process a value of pi volts because pi has infinitely many digits, which we won't be able to store. But we would need to cut it off after a certain number of digits. For a decimal number, for example, we would say we only have space for like 2 digits after the decimal point, so we could only store 3.14 instead of 3.1415926, whatever for pi. So this is this transformation, the second transformation we have to do here. We have discrete times now, and now we also need discrete values on the right-hand side. And this is done by what's appropriately called an analog digital conversion, or simply AD conversion. Now, AD conversion is a very important part of sensorics, and so appropriately, there's a large number of different methods that have different properties in terms of quality of the signal, in terms of speed, in terms of cost. So we're not going to introduce all of them. We're just showing you some examples of AD conversion here. So this is a very common AD converter, and this is a generalized abstracted circuit diagram. And this is a so-called flash AD converter. It's a flash AD converter because it's fast, because it can convert whatever, one sample every, if it's clocked, every clock cycle. And what we do here is we have a voltage signal, h of t, coming in on the left-hand side. So this is our time discretized signal here, which still has continuous value domain. And we have a reference value voltage. So this reference voltage should be higher than the highest voltage in the signal we want to digitize. And what we do here on the left-hand side, you see 4 resistors R. These resistors all have the same size. So if we, and of course we have ground on the bottom. So if we have a reference voltage going in on the top, and we have four resistors here, then we divide our voltage into four equal parts. So essentially, a resistor has results in a voltage drop, and each of these resistors, 1/4 of our original input reference voltage drops. So essentially, if we have 5-volt Vref on the top and we have 0-volt ground on the bottom, then we have steps of 5-volt divided by 4, so 1.25 volts each. So on top of the bottommost resistor, we have 1/4 of the reference voltage, so 1.25 volts. On top of the second resistor, we have half of it, so 2.5 volts. On top of the third resistor, we have 3/4, so 3.75 volts, and we have Vref as the highest reference voltage on top. And what we do now is we provide these different voltages, so 1.25, 2.5, 3.75, and 4 voltage, 5 volts, to these triangles in the middle. So these triangles are what we call comparators. So these compare two voltage levels. So these fixed voltage levels, because the reference voltage is fixed, these fixed voltage levels are provided to one input, and our signal that we want to sample, that we want to digitize, is provided to the other output. So we just compare. And let's say we have 3 volts h of t at the current moment. So this is time discretized, so we have some time to convert it, right? So it stays constant. So we have 3 volts. So our topmost comparator says 3 volts is less than our reference voltage of 5 volts. So you get a 0 here at the output of our comparator. The next one compares our 3 volts to 3.75 volts. This is still less, so you get another 0 in your encoder here. The next one compares it against 2.5 volts, and 3 volts is larger than 2.5 volts, so you get 1 at the output of our third comparator here, and our bottommost comparator is at 1.25 volts, so 3 volts is obviously also larger than 1.25 volts, so we get another one. So our signal going into the encoder is read from top to bottom 0011, and this encoding now, this is not a digital number, this is just a number of comparison steps. So these steps, as shown on the right-hand side, we essentially count the number of ones here in a so-called priority encoder, and the number of ones gives us a digital value. So for example, a voltage between 0 volts and 1.25 volts would be encoded as 000 as a number. A voltage between 1.25 and 2.5 volt would be 001. A voltage between 2.5 and 3.75 volts would be 010. And the next one would be 011. And you can see this is only 4 steps. So this is very coarse. Uh, of course, you can just extend it. So you can have more resistors. So you divide your reference value into more and more smaller steps. You can have more comparators and a larger encoder. And this gives you more bits at the output. But this is very expensive. So we need 4 comparators here to get more or less a bit more than 2 bits of output here. And this is essentially a power of 2 thing. So if you want to have something which is usable for audio signals, so a 16-bit value, then you need a whole lot of comparators on the left-hand side. And this is on the one hand very expensive because it takes a lot of area on your semiconductor, and on the other hand, it also requires quite a lot of energy because this voltage reference is divided all the time. So when you apply a voltage across a resistor, there's a current flowing, and this resistor converts this energy to heat. So essentially, your chip gets very hot and consumes quite a lot of energy. So that's why when you have very fast and precise flash AD converters, these are usually in a ceramic package to better dissipate heat and are connected to very large heat sinks. For example, in high-speed cameras, things like these, where you need a lot of these things for different colors of the video signal, for example. So this can get expensive quite fast. But of course, this is a very fast converter because these comparators work almost instantly, and the encoders can also be made pretty fast. So if we have an AD converter, the question is, which precision do we get out of it? So that's what we call a resolution in bits of an AD converter, which is the number of bits produced. Now for this, we can also look at the resolution in volts. And we've seen this is the difference between two input voltages, causing the output to be incremented by 1. Or on the other hand, or if we look at it from another point of view, that's exactly the voltage that drops over one of our resistors in our voltage divider. And this resolution Q in volts appropriately is our reference voltage. So the difference between the largest and smallest voltage, for example, 5 volts to 0 volts, divided by the number of voltage intervals or the number of resistors in our divider. And that's the resolution in volts per step. So if we had 5 volts in the initial example here on the previous slide and 4 resistors, we would have a voltage resolution of 1.25 volts, which is not a lot. But maybe for some signals it's enough. Now, if you want high resolution of an AD converter with low cost, you can also use a method which is called successive approximation. So this really reduces hardware costs by just using one comparator. And what you do now is you actually provide this comparator with successively changing values to compare against. So we don't have fixed values, which we provide by a fixed voltage divider, but we now generate the values to compare against. So we start again with our time discretized input signal h of t, and this goes into a set of control logic, which stores if the current value is higher or lower our comparison value. And then we do something which you probably know from computer science. We do a binary search. So if our signal value h of t is larger than our comparison value, so we start somewhere in the middle of the range. If it's above the range, then we just look at the top half of the range. If it's below the range, then we look further in the bottom half of the range. So we adjust the voltage to compare against appropriately, convert it again to an analog signal using a process called digital analog conversion, so the opposite of our analog digital conversion, and then provide that value to our comparator again to the next step here. And this is very efficient because you only need one comparator here. You only need a number of bits that you can store and a DA converter. But the problem is, well, it's slow because you have to do it in separate steps. These steps take some time, but you can have a very high precision using this. And this is a principle that shows how successive approximation works. So we start off with our signal to compare against, so the signal that's provided at the minus input of the comparator at the red line. So we start in the middle of our possible voltages, and Vx is the voltage we want to digitize. So we start and we figure out, we look at the signal, our red line, and our black line, and we see the black line is above our red line, so it's in the upper half, so the first bit is a 1. And then in the next time step, we just look at the upper half of the interval and we split it in two again. So now we look for our upper interval. Is our black line now above or below our red line here? No, it's below our red line here. So essentially it was turned into a 0. Then we look at the next interval here, which is in between. So the interval going from 1/2 to 3/4 of the maximum voltage. And we can now check in which interval it's here. And again for the fourth step. And we could continue if we had a higher resolution in bits and a good DA converter here. So you see it takes more time because we have to do it in steps, but it's much less expensive because we need only one of these expensive comparators, and we don't need any of these voltage dividers on the chip, which are also very energy consuming. Now, of course, this is only a very, very quick overview of analog to digital converters. There are a large number of other types and techniques for building converters. So this is just an overview of what's available with different parameters. So you can have very slow AD converters. So on the x-axis, we have the input bandwidth that's possible in megahertz. And on the output, we have the effective number of bits at the given bandwidths. And very slow ones, so working at maybe kilohertz or less, are so-called integrating types. So they have a capacitor which you charge for a certain amount of time, and then you measure the voltage at the capacitor. And that can take some time. So this is used for whatever DC signals, for example, in a multimeter, so in your handheld measurement device, where you only want to check is this a 5-volt supply or a 3-volt supply. This is not going to change then there's other types. We've seen the successive approximation AD converters, which somehow work from an input bandwidth of like 10 kilohertz to a megahertz approximately. So that would be very useful for audio signals. And they give between 10 and 15 bits of usable bandwidths. And you see at the very top end are our flash converters here, which can go from 10 megahertz to hundreds of megahertz. But due to cost and energy restrictions, actually the number of bits you can really use is quite constrained. And there are a number of other converters. So if you're really interested in these, please feel free to look them up or look at the reference we've given here. Right. So what we have achieved now is we have a signal that's time discrete and value discrete. And of course, if we have discrete time steps, we can ask our computer to read a value at these discrete time steps, and that's exactly the digitized amplitude, the digitized value we've just produced using our analog digital converter. So now we just have an array for each time step, and in this array, we have a digital number representing our digitized value at that point in time. All right, so everything's fine, right? We can use this right away. Well, there's a number of problems, obviously. And one of these problems is what's shown in the IoT data processing layer here is that these signals are not ideal. And one of the parts of IoT data processing I'd like to discuss here is how to get noise out of the signal. So how do we get noise into the signal at first? Now, first, the problem is that AD converters aren't perfect, so they're temperature dependent, and especially the least significant bit for this is just a very small voltage which can toggle there. So maybe these bits can toggle between 0 and 1, even if your voltage is constant, because it's just on the border somewhere. You can have what's called quantization noise. We'll discuss this in a bit more detail. And of course, you can have all sorts of circuit problems like imperfect designs, imperfect PCB layouts. You can have a faulty component that's temperature dependent. You can have loose connections like bad soldering, or you can, of course, have electromagnetic interference. So some other signals, radio signals, or whatever, disturbing the signal you're going to measure. All of these are noise. So noise is just a part of the signal that shouldn't be there, but it is there. And the question is how to get rid of it. So any digital or analog process which produces or essentially consumes the signal is vulnerable to noise. And this denoising is a very important processing step. We won't go into details here because otherwise we'd spend a semester on signal processing, which is interesting in itself. But just you should know that there are different ways to actually denoise a signal. And you can do it in software. So one very simple thing is a rolling average. So you don't only look at the current measurement value, but for example, you look at the last 10 values, and then you take the average of the last 10 values and replace the current value you're looking at with this average of the last 10 ones. And this means that very high frequency changes in the signal, which is usually low frequency, they are mostly removed and flattened out of our signal. So this, what we call the sliding window of the n consecutive signals, is very easy to implement because you just have to add up these values from the last 5 samples in your array and then divide them by n. And this is your new signal for the current sample. And then you go to the next sample, take the previous 10 samples again, and so on and so forth. You can also do something that's a convolution. So here we apply mathematical functions and try to integrate over a function. Or as we've seen, you can apply filters, and these filters can not only be in an analog nature, but they can also be implemented using digital signal processing, so using numerical methods. And you can build something like high-pass filters, which only pass frequencies above a certain limit. You have low-pass filters, which block all frequencies above a certain limit, or you can even have bandpass filters that either filter out a certain range of frequencies and remove them, or filter out everything outside of a given range of frequencies. So all of this is possible, and if you want to design an IoT node with certain sensing capabilities, you should be aware of all these effects. So designing IoT nodes is nothing for a computer scientist alone. I'd say you need an electrical engineer and ideally one that has also some experience in the analog and signal processing domain. So that's what makes it difficult, and especially if you don't have analog filtering, then you might need to provide digital signal processing in software. So very many processors nowadays, like the ARM Cortex-M4, have so-called DSP extensions like multiply and accumulate, which serve to accelerate digital signal processing here. And you might have to use a library or even to implement methods yourself to filter the signals to get useful values out of your sensors in the end. So one sort of noise is one we are unable to avoid because this is implied by our AD converter, by the quantization that's happening there. So quantization noise is essentially an approach to model the quantization error that's introduced by the AD converter. So an AD converter only has discrete time and value steps, as we've seen. So at all points which are not exactly the sampling intervals, so the sampling points in time, we have a difference between the original signal, the analog signal coming in, and the signal we are reproducing. So this is shown on the right-hand side here. Our red curve is the original signal coming in, our h of t. Our sampled signal here, we just assume a rounding or truncating of values towards zero, is our green step function here. And you see at the sampling intervals, it just barely touches the original signal, and otherwise it's always a bit away. And what you can do now is you can just subtract both functions from each other. So you can calculate h of t, our original analog signal, from our sampled signal w of t, and what you get is the blue line. And this blue line is essentially noise. And you might have heard this noise if you have used MP3s many years ago to save space on your precious SD cards, which were very small back then. You tried to sample signals not only with a low sampling rate, but also with a low number of bits. And for example, if you sample audio signals with 8-bit only, this is not really enough to reproduce, for example, music with high fidelity. So you hear this noise as audio noise, as audible noise, and this is exactly what happens here. So you cannot ideally reconstruct the signal, so you have this difference to the original signal, and that's what you hear is noise in your speakers or in your headphones when you have a signal with a low amplitude resolution, for example. This is exactly this blue line of difference what you're hearing. And this is unfortunately also nonlinear and signal dependent, so it's not easy to compensate for it. So people spend years and years, like the Dolby company was doing denoising stuff, and invested millions in just building better denoising algorithms, for example, for audio signals. And if we have an ideal ADC, so this is not temperature dependent, for example, which makes it easier to calculate it, we can actually calculate the ratio of signal to quantization noise, SQNR, and this is essentially 20 times the decimal logarithm of 2 to the power of quantization steps, or around 6.02 times the number of quantization steps. And this is a virtual unit called decibels, you might have heard before. So this just gives the relation. So essentially, this is just a number because we just divide a signal which has volts by another signal which has also volts as a unit. So we just get a raw number out of it. But since raw numbers are confusing, this pseudo unit was called bells or then decibels, which is a logarithmic measurement unit for this relationship between two signals. So this 6.02 is something you see very often when you talk about quantization, AD conversion, and so on. So you know that the max SQNR for a 16-bit analog to digital converter, which would be useful for audio, would be 6.02 times 16 bits, so quantization steps, and this would be 96.3 decibels. So if you now hear about the decibels of your amplifier and the precision, maybe you have a bit of a better idea what this is actually all about. So it's all about noise and getting rid of it. And here's just an example of a real-world quantization noise for an audio signal. So the signal to noise ratio again is 20 times the logarithm of the effective voltage of the incoming signal divided by the effective voltage of the noise. And for an ideal n-bit converter, this is n bits times 6.02 plus some basic level of 1.76 decibels. Again, we're not going into details here. So a 16-bit converter can give you a quality, so a signal-to-noise ratio of at most 98.1 decibels, whereas if you invested lots of money in your audio equipment for a 24-bit converter, you would get a signal-to-noise ratio of around 160 decibels. But then you would have to spend quite a bit of money. So professional audio equipment usually uses 24 bits, consumer audio equipment usually uses 16 bits. And if you hear about 1-bit converters and 1-bit audio technology in your CD player, then that's because they use something like successive approximation and very similar methods with the AD conversion we've seen before. Of course, we have usually non-ideal converters, so these numbers for the signal-to-noise ratio, these decibel numbers, are usually not achievable in real life, but they're a bit lower. Right? So, enough with all the physics, right? Not quite. Sorry. We have to look at another dimension yet. So it's a dimension we've looked at before. It's time. But now we need to look at time in different IoT systems. So we've seen at the beginning that fusion of IoT sensor data is very useful to increase the precision of data or to get a different view of data or of the physical effect that we want to observe because we apply different sensors. So we might apply an ultrasonic sensor to measure a distance and also a 3D camera or a LiDAR. And if we combine these data, we can actually have a better precision because an ultrasonic sensor measures at different frequencies, so this might not be reflected by something that a laser from a LiDAR might be reflected from, so you get better information. So sensor data fusion, you have different IoT devices measuring the same physical effect with different sensors, and then you have to combine all these things. And so this is a very important step to improve the quality of data in IoT systems. So as I said, one sensor is not enough. We want to have this sensor fusion, and this leads to less uncertainty than what would be possible when we just have individual sensor sources or just a single sensor source. So one example would be to obtain a more accurate location estimate if we're indoors somewhere in a building. And you can do this by using Wi-Fi localization signals, so triangulating signal strengths between your Wi-Fi access points that are distributed throughout your buildings, and additionally use a camera stream of a camera to figure out where you're going, how fast you're moving, and so on. And the challenge in IoT devices is that the IoT is a very distributed system, of course. So we have very many systems that have to capture data, that have to send out data, and this data has to be combined. So the different sensors of our system, which we want to fuse, are very often located on physically different devices. And uh, in order to fuse these into useful data, we need to assure that the data samples we're going to fuse were taken at exactly the same physical instant of time. So if you fuse sensor A, a signal, with a signal from sensor B that was taken 5 seconds later, then of course, if we have a moving object, that object would have moved away from the one sensor and maybe in relation to the other sensor. So we get a signal that's not very useful. And this same instant of time doesn't sound so critical, but it's actually a relatively complex problem. So, uh, first, to do the value fusion, there are a lot of approaches based on, for example, statistics and filtering to fuse the information itself. So different sensors differ in precision, in quality, in computation and memory overhead. I will just give some points here of techniques which might be involved, starting from relatively simple things like using classical statistics and the central limit theorem over Kalman filters, Bayes networks, Dempster-Sheffer theory, and going into more complex things like fuzzy logic and even something that's of course very much discussed today, neural networks for fusing sensor data. Now, going into detail here isn't really feasible because there's so many sensors out there, there's so many different values that can be produced, so we need to leave it at this short yeah, list of different methods here. And if you're interested, please take a look at literature reference 6. But one point I want to discuss, and which is very much feasible in IoT and in software, is actually the question of how to fuse or how to enable these sensor data that you want to fuse, how to guarantee that they are taken either at exactly the same amount in time, or if you need to order things, that you can guarantee a certain order of signals that you're going to measure. And that's an important thing in itself. So here we have an example of the Eurofighter fighter plane, and this has a large number of sensors. And you see on the lower left-hand side here, you see that these sensors actually cover different ranges. So fusing these sensors makes sense. So you have a fast, large range infrared sensor, which is this dark blue narrow triangle in the middle. So it just doesn't have a large angle. It doesn't have a great resolution. Uh, but if you combine it with a radar, which has a much larger angle, so the light blue thing here, and a much higher bearing resolution here, then you can combine it to get a better view of your environment. And this sensor fusion, and of course you have many different sensors in here. Again, I'm not an expert in fighter planes, obviously, so we have to trust this diagram a bit, but this helps tracking, for example, enemy airplanes in your fighter quite a bit better than if you had to rely on infrared and radar alone, because these signals cover different ranges, cover different angles, and so on. And so these are combined in this very expensive piece of equipment, obviously, in order to give a pilot a better view of what's going on in his or her environment. Now, we're not going to build fighter planes, I think, but let's talk about the timing effects. So how can we actually ensure that if we have multiple samples, or if we have samples coming in from different sensors, that we can actually combine two samples from sensor A, one from sensor B, which are taken at exactly the same point in time. So time is a very difficult problem in distributed systems like our IoT, and I would like to refer you to the Distributed Systems textbook by Josh Coloris and colleagues, which is one of the standard textbooks on distributed systems here. And chapter 14 gives you much more detail about time in distributed systems than we can do in the amount that's available here. So the background, the general problem we have is that in a distributed system, we are missing coordinated information about the current time. So every IoT device has its own idea of the current time. And of course, we can synchronize clocks. So we can say we boot up all devices at the same time and they start with a given clock. And this is identical for all the devices. The problem is that these clocks drift away from each other of the time. And you know this with whatever your watch and your clock and your phone and your clock on the wall. Like after a couple of days, even if you synchronize them at the start of the week, after a couple of days, uh, if they're just left alone to run alone, they all show a different time if you look at them at the same point in time. So they drift away from each other. And essentially, if we augment each of our sensor values locally on a device with a local clock with a timestamp, these timestamps would seem identical, but would in fact indicate different physical points in time. And then we would fuse the wrong data and would get, in the best case, just some imprecision, so some noise again in our signal, or in the worst case, just complete garbage out of it. So the background problem, as we've seen, is missing coordinated time information. And what's the reason for this? Now, the source of the problem is what we call clock drift. So, a clock in a computer is controlled by a small electronic component, which we call an oscillator. So, an oscillator can be built in different ways. Very often, it's built from a quartz crystal. So, a quartz crystal has a regular crystal structure. And if you apply a current to this quartz crystal, it starts to swing. And the frequency this quartz crystal swings at is predetermined by the properties of its crystal grid inside of the crystal. And for real-time clocks, we often use a given frequency. For example, most of them use 32,768 hertz. Now, the problem is that's what we hope. This frequency is not 100% precise. It's dependent on the temperature. So of course, if it's warmer, then maybe, yeah, due to physical properties of expanding or contracting, your crystal grid might have slightly different distances, so it swings at a slightly different frequency. It might be related to aging, so some connections breaking down maybe, or even manufacturing variability and so on. So link number 8 gives you some background on this. And typically for a quartz crystal, with a frequency tolerance of which is usually in industry of plus to minus 20 parts per million, we can have an oscillation frequency at a constant temperature of 25 degrees centigrade between 32,768.65 and only 32,767.34 hertz. So that doesn't sound much. I mean, it's like not even 1.5 hertz of difference. But if you just look at these extremes, so you have two systems as shown on the left and right hand side here, both with a quartz that nominally ticks at these 32,768 hertz, but in fact ticks at different frequencies, then these two clocks, when you synchronize them at the start of the day, they can differ by around 3.5 seconds in one day already. And of course, if you want to measure high-speed effects, 3.5 seconds, for example, if you want to detect whatever cars driving by, well, 3.5 seconds is quite a bit of time, obviously. So we need to do something about this. What do we need to do? We need to synchronize the clocks more often. Uh, Now here we can have different requirements. First, we can just imply that we really want the absolute time to be identical, so the view of the absolute time to be identical on all of the nodes in our distributed system, so on all of our IoT nodes, to really figure out the exact point in time which is consistent over all of your systems at which an event like a sensor measurement occurred. Or a weaker form of this is just the order or relative time. So did one event occur before or after another? And an easy way to do this, which is used in some IoT solutions, is just to use GPS. So GPS, our global positioning system, as you probably know, consists of a number of satellites in a geostationary orbit. And these satellites are provided with atomic clocks, so high precision clocks, and they synchronize with each other. And what you do is you do a triangulation of different signals of different satellites. And this not only helps you to find out your position, but you also need this precise time to figure out the run times of your signal from the satellite to where you are on Earth. And these differ uh, related to the position of the respective satellite in orbit. So you can figure out how long the signal takes from satellite A to you, satellite B to you, satellite C to you, and then you have essentially a circle on the Earth where you're located, and then if you have an additional satellite, well, you can figure out your exact location. That's, of course, a very quick description of what's going on. In fact, it's more complicated. So we could equip each of our IoT nodes with a GPS receiver. Now, GPS receivers have come down in price significantly due to mobile phones, but still they are relatively expensive and they're energy hungry. And of course, they don't work in certain conditions like underwater or inside of a building. That's very difficult to operate. So if you have hundreds of IoT sensor devices or you're operating in circumstances where you don't get GPS reception, that's not a really viable solution. Of course, we need to add there are competing technologies like the European Galileo or the Russian GLONASS system, and I think there's also a Chinese one, and these work on very similar principles, so they also provide synchronized times. And what's funny, of course, in the end, well, we're measuring time. It's also just an effect you measure, a physical effect. So GPS and the related systems are essentially just a sensor fusion network itself, and the sensor fusion happens inside of your GPS receiver, which has to actually triangulate the radio signals coming in. So that's a solution that might work for some use cases, and that's an easy solution because the precision of the time provided by GPS is very high. But it's a costly solution and does not work in all circumstances. So are there alternatives? Yes, there are. So we have network devices. So the question is, can we just simply synchronize clocks over the wireless networks? So let's say we have one definitive clock source, one authoritative clock source, which we call our time server on the network. And this just distributes the time information over our wireless networks to all the other nodes. And then it does this regular every second or something like that, and we're happy. Does this work? Well, it has some problems. So, for example, the time for a signal to propagate from the time server to your clients might differ because some of the clients might be closer to the time server, some might be further away, some might need a retransmission because a packet was lost or disturbed or something like this. So, when you send out the information, it's 12 noon 000 right now, then, at the point in time it arrives, maybe to the left system, to IT system number one in our diagram, it takes 10 milliseconds, so it's already 10 milliseconds late. So it has a different view to the time server. And on the right-hand system, IoT system 2, it takes a bit longer to propagate. It takes 15 milliseconds. So even though we try to synchronize the information by the time the signal arrives at our IoT systems, which are supposed to synchronize the time, both systems are already 5 milliseconds out of sync. Well, that's a problem. So the solution is to try clock synchronization algorithms. These have been invented already to synchronize early machines in the 1980s over the internet. And there's things like the network time protocol, which is an RFC, which we linked here. And these used a relatively simple algorithm. And one of these is the so-called Berkeley algorithm. And just in simple terms, the Berkeley algorithm actually has an additional functionality on the time server. So the time server actually requests whenever it sends out timing information to a client, it requests a reply. So it measures the time from sending out the time information to receiving the reply. And this is what we call the round trip time. So it goes from time server to client and back. And then we divide it by two. And we assume, that's just an assumption which mostly works, that the time to transport a packet in one direction is equal to the time it takes for the packet to come back. This is not always the case, but it works pretty well. So if we know the round trip time, we know the actual difference of time, the IoT system we send the time information to would see. And if we know this, we can send something like correction numbers to these different IoT systems. So we can tell the other IoT system like, okay, you need to correct down, like the left-hand system, you need to correct your system, your clock down by 10 milliseconds, and it can send to the right-hand system, you need to correct it down by 15 milliseconds. So these clock times are averaged, you're ignoring outliers, and the differences to adjust are distributed for each client, and it distributes the differences instead of a new absolute time, because a new absolute time would have the same problems as the initial one. Now, there's one challenge here. What we cannot allow is to have a clock going backwards. This would mess with most of the software because most software assumes time is moving forward. It's not stopping, it's always moving forward. And when we have a time of 12 o'clock, it's not suddenly 11:59 a second after. Well, that could happen if we had a larger just value here. So essentially, when we receive the information, okay, we need to go back 10 milliseconds, we're not just setting the clock back 10 milliseconds, but we let it run slower for an amount of time until we caught up with this 10 milliseconds that we have to catch up with. So this monotonicity in time is something that we have to take care of because negative adjustments confuse so much software, not only when we switch from summer to winter time, but especially then. Time would appear to run backward, and software just isn't made for this. So this is a very simple method that actually works pretty well for, yeah, given amounts of time where these assumptions hold, that the round trip time can be halved and that the round trip time is relatively constant over our network. I just wanted to present you one additional approach, which is a bit easier to implement, but which has not these high guarantees. So this is by Leslie Lamport. You might know him as the inventor of LaTeX, so the macro set that made Donald Knuth's typesetting system useful. And in general, he's a computer science researcher working at Microsoft, as far as I know. And he's working in real-time distributed systems theory, and here he considered the problem in the 1980s of just the ordering of events. So, did one event happen before or after the other? And if this is important, we can use Lamport's logical clocks, and these are able to derive a partial ordering of events with very minimal overhead. So, the basic idea is to introduce an ordering that's called happened before between different processes or different systems in our IoT, which we call PI. So I is just the index of a process running on one of the nodes. So if we know that we have two events that occur at the same process, so in our case on the same IoT node, PI, then we have an order for these two events, and we know because they are measured on the same device that they also occurred in the order in which they are observed on this device. Now, whenever a message is sent between processes or devices, in our case of the IoT, then we know the order of the event and the sending of the event. And we always know that the event of sending a message has to occur before the event of receiving the message on the other end because it takes time to send a message and it cannot go back in time. And logical clocks are now a simple mechanism which make use of this happen before ordering and of this knowledge on a local machine and on the ordering when we send messages. And that is something we can capture numerically by something very simple. So we have a monotonically increasing counter in software, which we just count up. And this is just a counter whenever something happens. So this value does not have to have any relationship to any physical clock because we only want to know if something was earlier or later, but we don't want to know how much it was early or which point in time it was happening. So each process or each node PI keeps its own logical clock here. And now processes increase this counter, so update their logical clocks, transmit values of their logical clocks in messages to other systems. And so the first thing is a logical clock of a node I, which we call Li, is incremented before each event is issued at this process Pi. So we just increment our logical clock before the next event. And now when we send as a process PI a message M, then we don't only send a message in our distributed system with with data, we also transmit this current counter value, which we call time. It's a logical clock. It doesn't have to have any physical relation, as we said. We just transmit this current counter value. And if another process Pj now receives this message M with the additional logical timestamp T, then it checks its own timestamp. So is its own timestamp actually larger than T or smaller than T? And it takes the maximum of both values. So its logical timestamp on its own machine and the one it received from the other one. And then again, it applies LC1, our first step, before timestamping the event of receiving this message, because some time must have passed before between sending and receiving the message. Now, this is just a very short overview, but I think it's an interesting alternative. And this goes much further. So there's an advanced method that was introduced called vector clocks, which is also used in some distributed systems applications. So I think this is still some research related stuff in IoT here. I haven't seen this applied much, but since I have some background in distributed systems theory, I thought I'd present you these interesting links here, and maybe they will be useful for some of your days later, or maybe they give you some interesting links or motivation to look into a distributed systems course also. All right. So this was a lot of theory. This covered very many different things from physics to numerics to signal processing to logical clocks to time. What can we conclude? What have we learned today? So we have learned that much of the data in IoT systems is obviously derived from the sensor data we read in our IoT nodes. And we know the analog sensor data has to be digitized, so we need to discretize in the time and value domains. And we use this using a deconverters, sample and hold circuits, and filters for the digitalization of time and values. Experience in signal processing is very useful for building IoT systems that really capture high-speed data or data that has to be very precise because you have all these effects like aliasing or quantization noise when you have high-speed signals. Of course, if you only measure temperature, which changes very slowly, and you only need it to a degree or something, it's not quite that critical, to be honest. Nevertheless, we've also seen that sensor fusion in general can be very fundamental to improve the quality of data in IoT systems. And we've also seen one specific point here, time synchronization, different approaches to do this, to find the sensor data values that actually happen at the same point in time on different IoT nodes for different sensors. And we can also have these algorithms for clock synchronization then, or we can have these simpler algorithms which just provide information about the order of events and not absolute times. So this was quite a lot in this first lecture on data in the IoT. In the next lecture, we go and take a closer look on transfer of data on joint protocols, like for example JSON, to transfer and process data in a common format on the IoT. So thanks for listening today. Thanks for joining today. And here's a list of references for you if you want to dig deeper, as always. Thanks again, and until next time. Bye.